Finished up. We talked about intermolecular forces, and we talked about acids and bases. There's an extra definition that I kind of want to add to your acids and bases. So first off, which of these two definitions is for an acid? Hydrogen ion donor or hydrogen ion acceptor? The hydrogen ion donor is your acid, and your hydrogen ion acceptor, why does it look so weird, is a base. Sorry, something just looks wrong. The one extra definition I want to address here ultimately comes back to the hydrogen ion. Okay, so it doesn't really matter which one we look at, it's going to hold the same. We can define that differently. Instead of calling it a hydrogen ion, okay, we might change how we reference that. Anybody know how we refer to it differently? Okay, well, let's come up with another idea. What makes a hydrogen atom? What's that? Yeah, hydrogen, that was the common answer on Tuesday in the afternoon. I just forgot to tell you guys about it. What are the subatomic particles that make it? So in a hydrogen atom, we have one proton and we have one electron. No neutrons, and we know there's no neutrons because if you look at the mass, it's only one. Okay, so there's no neutrons in a hydrogen atom. If we make it a hydrogen ion, what do we do? You get rid of the electron. If we make it a hydride ion, that's when it gains electrons. But hydrogen ion is where it's lost that electron. So what makes up a hydrogen ion? One proton. So what's another name that we could give to a hydrogen ion donor? We could call it instead a proton donor. Okay, so your acids will sometimes be referred to as proton donors, and your bases will typically be referred to as proton acceptors. Okay? I would argue the main reason we've switched that definition is hydrogen ion is an awful lot of syllables, and proton is, I guess, one syllable less. So it goes back to that whole chemist being lazy phenomenon. Okay? One thing to kind of be aware of while we are looking at that as being a proton donor or a proton acceptor, where is that proton going? Is it going into the nucleus? No, it's being attached as a bond on the outside, so you could see it almost as a floating proton on the outside of that. So when we think about proton transfer, we're not talking about a proton moving into the nucleus. We're talking about a proton forming a bond to that other atom. Okay, so that's why it's better to think about it as a hydrogen ion instead of that proton. Okay, questions about that? Okay. Some other things that we could mention along these lines, particularly if you think about the lab, for those of you in Tuesday lab, might be able to answer this better. If we're going to look at an acid, okay, what things do we need to see? You're given a random structure and say, tell me, is this an acid or a base? Okay, we need to see a hydrogen. So here's a structure. Let's take a look at this guy. Is that an acid? See plenty of hydrogens. So should we refine our definition? It's not just that we have a hydrogen. Good call. Okay, I'll accept that. Is it an acid now? Still not. Okay, so you're right. It does need to be aqueous. It does need to have hydrogen. Why is this still not an acid? Okay, when we're looking at our acids, as far as this class is concerned, if you have an acid, where is that hydrogen shown? It's out in front of the structure. Horrible definition, but it's a simplification of the rules that allows you to get through this class and recognizing your acids without having to understand as much about those definitions. So when we're looking at trying to identify a compound, if it's an acid, we will find a hydrogen, it will be aqueous, and that hydrogen will be in front of the formula. If those rules are not satisfied, we're not technically looking at an acid. Okay? I'm seeing the puzzled look there. Do you have a question with that?
Me?
Yeah. Okay, that's fine. It's just the way I normally look, right? Okay. If you have to move into further advanced classes, you get into more detail on this acid-base definition. In fact, most of organic chemistry is based on acids and bases. Okay? So those definitions get expounded on a little bit more. You have to apply it a little bit differently, but it comes back to these same rules. If you have a hydrogen ion and it can be donated, we're looking at an acid. Okay? Questions about those two definitions? No question? The top one, we won't even consider that as a base. Okay, we'll consider that top one. So that's an interesting question. Let me switch that around. I'm going to change the colors up on it. Looking for a base. What do I have? C2H5OH. Okay. For it to be a base, it must accept a hydrogen ion. Okay. Well, anything that can accept a hydrogen ion is going to have electrons. So typically we would look at a base being negatively charged. Okay, and that's kind of our broader grand scheme of things as far as a base goes. For you guys, we tweak that definition slightly, and we tend to think more along the Arrhenius base definition. And the Arrhenius base definition said that bases were what? Anybody remember? That was the one that had the giant useless stamp on the top of it. They formed hydroxide. Okay, so when we added them to water, we got hydroxide ion. So this is a really common thing to look for. So if we look for a hydroxide ion, we look up here, name of that compound, sodium hydroxide. There's a base. Okay, so one of the things students tend to look for is an OH. Cool. I can kind of accept that. Except the issue now becomes what happens with this compound I'm now starring. ICOH, is that hydroxide? No. Right, for it to be hydroxide, what does it need to be bound to? A metal. Is it bound to a metal? No. It's not hydroxide. We're not looking at a base here either, within the limits of your rules.
So their bases are bound to metals?
So if we have a base, we'll see that hydroxide ion, and it will be bound to a metal. So that's kind of, as useless as the Arrhenius definition is, that's pretty much the one that you guys will work with because it's the easiest to manipulate without having to go into a lot more details. Okay. We could spend a whole lecture just on acids and bases. Okay. So that species that's now starred, our C2H5OH, is not a base, and it's not an acid as far as you guys are concerned. Okay? Other questions on that? Just move it out of the way. Okay? So we had our conjugate acids and bases. So if we went through and evaluated all of these and we defined our HSO3- acting as an acid, that means the H2O must act as a base, because we've said the HSO3- is acting as an acid. What do acids do? Donate hydrogen ion. So it has to lose a hydrogen ion. Our base has to do what? Gain a hydrogen ion. Okay? You'll notice that we're writing water acting as a base, even though it's not hydroxide with a metal. Remember, some things can act as bases that don't fit within that exact definition. So in this case, we've specified some extra information for you, telling you that one of them is an acid, which means the other one must be a base. Okay, so some of that information is provided. We can then predict those possible products that come out of that. Okay? We could also go through and evaluate that double-headed arrow. That double-headed arrow, or sorry, two arrows, means that the reaction can go both our standard direction, our left to right, and right to left. Which means when we look at this equation, where are our reactants? Both sides of the equation. Where are our products? Both sides of the equation. It is an extremely tricky concept, and what we're looking at within that arrow is equilibrium, okay? The balance of your reaction. Okay? We'll look at that on the next slide. The more important aspect here is that if we look at that reverse direction, we put it into our standard format where it's left to right, we can go through and predict what happens, again, by looking at those. One of the things that we could then define is comparing the similar species across the reaction. HSO3 minus looks an awful lot like what? RSO3 minus 2. They are related to each other. The bulk of the formula HSO3 shows up in SO3. The bulk of H2O shows up in H3O plus. So what we end up saying is that those are conjugate partners of each other. Okay, they're related. If we want to take that a step further, we can now look at their chemistry. If we take a look at SO3 minus 2, yes, it is the conjugate of HSO3 minus. But how would it act? What is its conjugate? Is it a conjugate acid or is it a conjugate base? Well, to figure that out, we could look at our reverse reaction. If we look at the bottom one, what did SO3 minus 2 do to go to, or to become HSO3? It had to gain a hydrogen, which means that species acted as a base. So we can refer to it as a conjugate base. It is the conjugate of HSO3 minus, and it will act as a base. If we take a look at H3O plus, it is, whoops, okay, cool, didn't go anywhere. HSO3 plus, H3O plus, okay, is the conjugate of H2O. Those formulas are very, very similar. Okay? The one thing that is different between them is where the hydrogen is. H3O plus will act as what to go back to forming H2O? An acid. So it is a conjugate, but at the same time, it will need to act as an acid. So it is the conjugate acid of H2O. So what we're trying to do is evaluate the difference across that reaction. Does it act as a base? Does it act as an acid to get to that other species? All right? The typical question that you'll see along this is given a reaction, what species is the base? All right, so if we take a look at either of these equations, it doesn't really matter. Actually, let me cheat. Let's look here, even though it says equilibrium. Within that reaction, identify the species that is the base. Are you going to ask the people around you too? Or not? You know,
It's
all
on
that.
the screen.
What species is the base? Hearing a lot of H2Os. You're half right. And SO3 minus 2. Just because it says base up there doesn't mean you were all right. The answer that I heard most people say was H2O. If we're asking for the base, it's any species that can act as a base. What does SO3 minus 2 act as? A base. It may be labeled slightly differently because we add that conjugate in there. Don't get confused by that conjugate. It is also acting as a base to do the reverse reaction. So when you're asked to identify the base, there's two species. There's one on the left side of the reaction and one on the right side. Okay? Yes?
What's a conjugate again?
The conjugate just means it's related to something else.
Oh.
Everything will have a conjugate. Right? So what happens if I ask now, because you're bringing up the conjugate idea, instead of asking for the base, what species is the conjugate acid? HSO3 minus. Does HSO3 minus say conjugate? No. It is a conjugate acid. So you have to specify that also. Okay? The reason why I'm really pushing this is that it is very easy to get these confused and say, well, only the product is the conjugate. That's not, well, that is technically true, but realize the product is not always on the right side of the equation. Because if we go back and look at our arrows, really when we think about reactions, we only think about them from left to right. So we'd say the right is always a product. But what's the issue? We also have that reverse arrow happening, which means our product is not just on the right side of the equation. It is also on the left side of the equation. So if I ask for a conjugate acid, yeah, H3O plus is a conjugate acid, but so is HSO3 minus. Okay? You have to specify both of them. Okay? I still will go on the record and say that is an awful definition, but that is definitely the way it gets tested. So you need to know that. Okay? So what's going on with that double arrow? Okay, it's kind of a confusing concept. Again, it's something that is taught pretty much all of second semester general chemistry. 152 is all equilibrium. Now, that's how confusing of a concept it is. Okay? And really what that equilibrium is saying is that we reach a balance between our reactants and products. Okay? And we're not saying that the concentrations are the same of each of our reactants and products. We're saying that the rate, okay, how fast we do the forward direction and how fast we do the reverse direction balance out. So it has to do kind of with a rate and not with a rate all at the same time. Okay, so the example we looked at on Tuesday was with, sorry, I got to zoom back out here, was looking at kind of a seesaw. Okay, and the example I gave you was where we had kind of equal parts on both sides, because that's the easiest thing to see. But what happens if I went through and put the seesaw, whoops, that's an eraser, the seesaw fulcrum right there? To make sure this balances out, what do I have to do? I need a lot more weight on the right to counteract that, right? Kind of the physics aspect of it. That's equilibrium. Where that exact little triangle is located is dependent on our equilibrium information. I can't spell equilibrium. Let me try that again. Equilibrium. I spell it better that time? I can't read. It's okay. Okay? So where we decide to, or where the reaction decides to put that fulcrum is what our equilibrium is talking about. We're looking at that balance between those. Okay? Well, Le Chatelier came along and made an observation on these reactions. Once a reaction has achieved this balance, okay, so the reaction pretty much gets to go through and slide that fulcrum to where it wants to be so that everything is balanced out. Okay, so we're going to have different amounts or different weights of products and reactants. In this case, which side of the reaction is favored? Which one do we have more of, reactants or products? Products. Okay? So we'd be looking at the reaction going completely towards our products, effectively. Okay? Once we've reached that point, and everything's now happy, and the reaction says, okay, everything is nice and balanced. Le Chatelier said, okay, well, I don't like things in balance. I'm going to mess with this. Okay? Because once everything's stable, once you guys understand the material, what do I go through and do? I add more material, okay, just to make things a pain. Same thing as what Le Chatelier did. He went through and said, okay, here's the reaction. You got it, settled, good. I'm going to mess with it. I'm going to add another brick over here. What happens? Now it goes out of balance. Right? Now there's too many products, and our fulcrum, make sure I'm doing this right, the fulcrum shifts. Okay? And we're now kind of rocked the other direction. Well, our reaction kind of has its own artificial intelligence. And that intelligence is, I want to be back at equilibrium. What does the reaction have to do to get back towards that equal balance? We need more weight on the reactant side to counteract that. Okay? But our reaction can't create matter. So how can it get more weight on the reactant side without creating matter? What it's going to do is take a chunk out of the product side and rip that little piece out and put it over onto the reactant. It'll run the reverse reaction. So now when we go through and take a look, what we've got is we've got that section now erased out, and we've now added that extra mass onto the reactant side. Now the reaction has reached equilibrium again and is now stable and happy. Okay, so Le Chatelier decided to test it again. Said, okay, well, if I added stuff to the products, it shifted towards the reactants. Well, now I'm going to add stuff to the reactants. Now what happens? It's again shifted out of balance. There's now too much reactants. So what does the reaction do? Gets a chunk from? Yeah, give me left or right. Okay, it'll take it from the reactant side and shift that back over to the products. And so what we end up with, see if I can do this right, shifting stuff over to the product side to then account for that balance. So again, I end up deleting that piece from the reactant, and that's trying to establish that balance between them. Okay? Kind of makes sense? No.
The reactant is enough to make a product?
So what we did is we put a whole bunch of reactants on it. So now there's too much reactants. So the reaction has to go, well, how do I get the balance back? Well, to get the balance back, I have to put some products down to lift that back up. Okay, but we can't create matter. So what does it do? To make those products, we have to get rid of reactants. So we make some of the reactants react with each other to make more products, to shift it over. So we're taking some of the weight of our reactants, a chunk of that, and shifting it across. We can't take the exact same piece because that's going to put it completely out of balance. Okay, it's only going to be taking small amounts of it, okay, to get to that equilibrium perspective. Okay?
So at the end, we have many more products.
At the end, we have the exact ratio, same ratio of products and reactants. The ratio is always maintained. That's what equilibrium does, is it maintains that ratio of reactants to products, or products to reactants, rather.
But they also have produced more byproducts?
Nope. The ratio is always maintained, period. Okay? If we look at just the amount of products, yes, the product amount will change. Okay, but that's not what we're asking about. What we're asking about here is the ratio between those. The ratio always stays the same. Yes?
So the reaction will just like keep going back and forth?
Keep going back and forth until what point happens? It's at equilibrium where it's balanced. We can't stop it. Okay? So the reaction will always continue. Once we've reached equilibrium, some products are making reactants, but those reactants are still making products. And so what's happened is there's now a constant flux back and forth. Okay? So back and forth between those. So what happened? I know that's a kind of horrible looking arrow, but that's an arrow. We went right to left and left to right. Does that look something familiar? That's the double-headed arrow that we put in our reaction equation. Okay? Our reactions are always going backwards and forwards. And that's why we use that double-headed arrow in our reaction drawings. Okay? It is a difficult concept. What you need to realize is that all reactions try to achieve equilibrium. Once they are at equilibrium, if we disturb them somehow, they will do whatever they need to get back to equilibrium. Okay? Another way to look at this, which might be a little bit easier, depending on whether or not you had maybe a good childhood with a seesaw or not, could switch this up and take a look at a chamber. Okay? And what we're going to do here, make sure this is open. we're going to take a look at a divided chamber. And what I'm going to do is fill this with water. Okay, I'm going to put water in on the reactant side. Okay, so as we start all reactions, we always just put in reactants. We don't put any products in, right? So we put reactants in. Okay? And let's say that we have some way of preventing the reaction from going forward. We don't, but let's say we do. So there's a divider now between the reactants and products. So I'm going to put in that many reactants. Now I say, reaction go. Oh, let's change this up. Let's make it more fun. Now you say, reaction go. Yeah, there we go. That's fun stuff. There we go. We erase the divider. What happens? The water is going to rush up to the other side. Until what happens? We reach a point where the water going back and forth is the same. And the water level is even across it. Okay? We've reached equilibrium. When we look at the water on the reactant side, that little molecule is still moving. It has an equal opportunity to be both a reactant and product, or on the reactant and product side. There is nothing saying it's in one spot or another. Remember, you take a water and you set it down. All of those molecules are still moving, which is a property of liquids. They constantly move. Okay? Yeah?
So you really don't know like where each one is at?
Nope. We don't know. Which is one of the things that makes chemistry both interesting and difficult at the same time. We're always trying to make sure that we maximize the amount of product. So we will try and stack the deck in such a way that we make more product. Okay? That our equilibrium favors product formation. Very rarely would we ever design an experiment where we don't favor the product, because we're going to run a reaction, we're trying to make something. If we don't make it, that was a pretty useless reaction. Okay? So we'll always try and come up with ways to adjust it. So one of the things that chemistry does is can go through and say, well, instead of these being equal sized chambers, I change the size of this chamber. Okay, what happens when you put a straw into water? It rises up in the straw a little bit. Okay, why? All sorts of complicated things go on with that. You're looking at surface tension, intermolecular forces, all sorts of crazy things. What we've effectively done is looked at a way of making our reactants form more products. Hence, our product level within the straw went up. So we can come up with ways to tweak the containers that hold each of these reactants and products, but we can't really control what's happening between the reactants and products. Those are all doing it all on their own, and we just hope for the best. Technology is now getting to the point where we can start to control single atoms. Once we have complete control over single atoms, we can make those atoms do what we want. We aren't there yet. Okay? So if you continue to process through chemistry, you might be one of the people that gets to do that. Okay? Which could be cool. Okay? So we're now at equilibrium. Everybody okay that we're at equilibrium within our water chamber? Okay? Let's be Le Chatelier and mess with it. What do you want to do? Let's add more water to our reactant. So we're again going to pause our reaction. So we'll put in that divider. And we put in more reactant. And now we say, I like the enthusiasm. Go, reaction, go. And what happens? It's going to, again, try and balance out. So what happens is our water level on our reactant will drop down a little bit, and the water level within our product goes up a little bit. Until, again, we reach the point where our purples are now going back and forth the same. What if we'd added it to the product side? Same idea. It's going to shift to account for that balance. So when we add that reactant, okay, when we tweak our system, we could add more reactant. What does that end up doing for us? That makes more product. That's one way we can take advantage of the chemistry, is we can stack what's going on the reactant side to help make more product. So we can maximize our yield of our product. There's another thing that we could do. Okay, it's really easy. okay, to add things, right? Think about all of the stuff that we've done this semester. Whenever we had a plus sign, everybody did a perfect job with it. When did we have problems? When we took stuff away, right? So let's go back to, again, saying, okay, reaction, you can't go anywhere. We're going to look at a new situation. This new situation, I'm going to take stuff away. I'm going to go into that product container, and I'm going to take all of that away so that the level is now down here. Okay. Now what do I tell the reaction to do? Go, reaction, go. Yay. Now what happens? It's again going to level out. How does it level out? The reactant shifts to fill the product side, and now our product level goes up. And our reactant level goes downwards. What did we just do? We reached equilibrium, but at the same time, we reached equilibrium by making more product. The goal of all of our reactions was make more product. So if we can set up a reaction and constantly be siphoning off our product, we can constantly be making more product, and we don't have to stress about equilibrium. Why not? Because our reaction never gets to equilibrium. It is constantly in a point of saying, crap, I need to get to equilibrium. I'm making more product, make more product, make more product, make more product. Until eventually what happens? There's now no more reactants to make products because we've entirely siphoned all the products out of it. Okay? So this idea of Le Chatelier's idea of this, looking at this equilibrium idea, is massively important because we can start to vary what's happening within our reaction to push one thing over the other. Okay? So kind of a neat concept. Okay? So you will see at least one question on Le Chatelier's principle, I believe, or equilibrium. Okay? So kind of watch out for that. Kind of a fun thing to play around with. I don't think I asked any questions about it because I didn't think it was going to be all that important. Then took a closer look. Okay? So it's kind of a fun one. If you have to go through and take 152, you all love mathematics, right?
Oh, yeah.
Yeah. That's all 152. Most people go in through first or 130, 151, go, oh, I can handle the math, it's not too bad. Then you get to 152, and usually half the class drops out because they realize they really don't have a firm grasp of mathematics. Okay? So 152 really, really hammers home a lot of mathematical principles, and we're going to talk about some of those towards the end of this as well. Okay? So now we've got an idea on what's going on with our equilibrium. So we can go back to our acids and bases. Okay, this is another fun concept. Strong versus weak. What just happened? Okay. When we look at our acids and bases, there's a couple of things to be concerned about. Thank you, Mark. We want to know, which did you use, a base or an acid? We want to know something about the strength of our acids and bases. If it's a strong acid, we should be really concerned about it. If it's a weak acid, we probably don't care. For instance, coffee. Anybody know? Acidic or basic? It's acidic. Okay? How concerned are you about splashing coffee on your skin? Depends on how hot it is, but that doesn't have anything to do with the chemical itself. Okay? One of the reasons why is that coffee is a weak acid. We aren't as stressed about it. Okay? Vinegar. Vinegar has what in it? Acetic acid. Woo, that's even named acid. We're really all that concerned about splashing vinegar on yourself. Probably not all that much there either. Why? So again, we're looking at a weak acid. So we've got a couple things that we could evaluate. This strong versus weak. Okay? The big difference between these is what happens when they hit water or when they hit your skin. A strong acid completely dissociates into the ions. Okay? So if we take a look at a classic strong acid, which one are you fearful of maybe? HCl. By the way, if you ever take organic chemistry from me, one of the things that you'll hear me ask is, what's your favorite acid? Okay? I don't care what acid it is, get one. Okay, it can't be LSD. It's got to be like a real acid. Okay, what happens when HCl hits water? It completely ionizes into H plus and Cl minus. Okay, we get those full-on ions. Those ions are what we're concerned about, and primarily the H plus. That's what's doing all the nasty chemistry to our skin. Okay, so that's what we're concerned about when we look at an acid. Is that H plus? Think back to the definition. What's our definition for an acid? Hydrogen ion donor. We're concerned about the hydrogen ion. Okay? So our strong acid completely goes all the way over to those ions. What happens if we take a look at a weak acid? Okay, you all remember the formula for acetic acid, right? Oh yeah, that's a good answer. We get H plus C2H3O2 minus. What happens in the case of acetic acid? Well, that sure looks like we get the exact same thing. We just talked about this concept of equilibrium, right? What happens in the case of acetic acid? It also does the reverse reaction. It only partially ionizes. Okay? We can actually add some more detail to this. It's not even just a perfect equilibrium. Most of it goes back to the unionized form. Very small amounts of it go to forming the ion. Okay? So we've got a strong versus a weak acid. So it's really helpful to know some way to define these. Well, a strong acid completely ionizes, which takes us to the definition of electrolytes. It allows for electric current to flow. If we've got ions, we've got something that we can pass electric current through. So a strong electrolyte, like your strong acids, will generate a lot of ions. So there we go, strong electrolyte. What happens with a weak acid or base? Well, they don't ionize as much. So depending on how concentrated our solution is, there's our next issue. Concentration, we might pass electric current, we might not. Okay? And that's all dependent on that equilibrium. Which side does the reaction favor? Does it favor the ions or does it favor our reactants? Okay? So now the fun part. How do we know the difference? I've got two solutions. Anybody know the color of HCl? Clear. Color of acetic acid? Clear. We've got two very clear solutions. How do we tell the difference? Okay. The way we did it in the old days, we probably had some slave and said, whoop, oh, yeah, that was the wrong one. Sorry. Okay. That's not a very good method. Okay. We don't use slaves anymore. That's not nice. Okay. We need to come up with some better way to define these. For you guys, we're again in this situation of how do we figure this out? Okay. Well, it's kind of a bit unfortunate because the way we would figure it out is by teaching you a whole lot more information about what's happening within each of these bonds. Organic chemistry. Okay? How many of you are taking organic chemistry? Yeah, so how many of you really care? That's what I thought. So how do we come up with that definition? Okay, yeah, again, these are not coming in right. We get strong acids, which we will define, and then we'll say our weak acids are everything else. Again, I don't know why it's not setting this up right. So your strong acids, you need to have memorized. You don't need to have them memorized for this test. But if it's 151 or 152, they'll make you memorize them. Some of these you already know. H2SO4 is sulfuric acid. HCl, hydrochloric acid. You're aware of some of these. Nitric acid, I think you guys worked with that. Those are your strong acids. What if it's not one of those acids? Then it's not a strong acid. It's by definition a weak acid. And then we'd have to understand something about the equilibrium to decide how weak or how strong. Our bases, very similar idea. What we're looking at is anything with hydroxide, back to the Arrhenius definition, where that hydroxide is bound to a group 1 or group 2 metal. If it's in that situation, we now have a strong base. What if it's not in that situation? Then it's weak. How about iron hydroxide? What do you think? That's an eraser. Stop giving me the answer already. Didn't write it fast enough. Those of you that can't put that one together, well, officially you couldn't put it together. Iron 3 hydroxide. Weak or strong base? I see hydroxide. That should suggest strong. What's my rule for strong? The metal must be group 1 or 2. Where is iron? Not in group 1 or 2. Is this a strong base? No. It's by definition a weak base. Okay? So that's one of the ways that we would kind of define and separate these concepts. Okay? So now back to our electrolyte concept. When we take any compound, something really messy happened with these slides. When we add any compound to water, if it completely, or if it ionizes at all, so by ionizes we mean do we get a cation and an anion, positive and negative charge, that positive and negative charge can allow for electric current to pass through the solution. Hence the term electrolyte. Okay, electrolytes are important to us. Okay, you think about physical activity. Everybody says, well, you got to replenish your electrolytes. Why do we need to replenish our electrolytes? Okay, so your muscles don't cramp. Why are your muscles cramping? We need the ions to pass across individual membranes within our muscles. Okay? There's a bigger issue than just muscles. How do we trigger that our muscles actually function and allow for these ions to pass back and forth across? There are nerves that run from your muscles all the way back to your brain, and your brain tells those nerves, hey, tell that muscle to release ions across it so we can actually do something. How does your brain transfer that signal down? It's ultimately electricity through electrolytes. If we don't have those electrolytes, little kids can't kick us in the stomach. Okay? Or in the knee, depending on how tall they are, I guess. Okay? So those electrolytes are really, really important for us as an everyday living experience because we have to be able to pass those charges through. If we have an ion imbalance, so some ions are more important than others. If you go back into muscles, it's not just random any electrolyte going across. It's sodium and potassium. Those are both positively charged. Why do we need a balance of those two? What's the difference between sodium and potassium? Take a look at your periodic table. Tell me. What's the difference between those two? They're even in the same row. How can our body cause our muscles to flex or move if we're looking at two ions, both of them with a +1 charge, both of them with the exact same chemistry? How does that work? Is there a difference between sodium ion and potassium ion? Someone might have actually said it. Size. NaCl, or sodium, is much smaller than potassium. Okay? The membrane where we're passing these ions across will only let the proper size ion transfer, which means we can build up a balance of sodium and potassium on opposite sides of that membrane. That imbalance is what our body uses to control how our muscles shift. Okay? Kind of neat. All based on size. Okay? So what we're looking at is this electric current. The compounds listed here are all strong electrolytes. Sodium chloride, you should remember. Why is sodium chloride a strong electrolyte? It's a salt. You've got to take it a step further, because I could draw another salt that's not a strong electrolyte, which is actually off the slide right now. Sodium hydroxide is also a salt. Why is that important? Yes? When we add sodium chloride to water, what happens? It does completely dissociate. That's what makes it an electrolyte. But why does it completely dissociate? How would we specify that? AQ as opposed to the other one. Don't check me on this one because I'm not sure I'm right. Why did I write a different phase? These are both salts. Let's pick one that I actually know is true. Then I'll feel better about myself. Why is silver chloride a solid, but sodium chloride is aqueous? They're both exactly salt. It's a metal and a nonmetal. Sodium chloride can dissolve, yes. Why does silver chloride not?
Because it's not
How do you know it's not soluble? Solubility rules. You can go back to your solubility rules and say, okay, should that salt dissolve or should it not? Okay? So all of those rules that we looked at within our double replacements now come back and shift into this new phrase or this new idea of electrolytes. Okay? So it builds, and it builds, and it builds. So you have to be able to constantly be referring back and looking at these. Okay? We even brought in the aspect of muscles, looking at biology. A lot of the theories that you see within biology are coming from chemical processes, size differences. You need to be able to take advantage of the information held within the periodic table, okay, and look at those size differences and apply them to those biochemical systems. Okay? H2SO4. Why does that completely dissociate into ions? Yes, it dissolves. H2SO4 was a strong acid. What do strong acids do? Completely ionize. They completely turn into ions. So it's an electrolyte, a strong electrolyte. What about sodium hydroxide? Why is that a strong electrolyte? It's a strong base. Strong anything completely dissociates into the ions. So we're applying those different definitions. Okay? We could go through and add in other acids. Okay? We could throw this one in just because it's dangerous. HF. Strong or weak electrolyte? How do you know it's weak? Because it's not a strong acid. If it's not a strong acid, then by definition it's a weak acid. Well, if it's a weak acid, that means it's also going to be a weak electrolyte. Okay? One of the things you'll find out when you get into the lab, so those of you from Tuesday lab might be starting to draw some parallels here, it's not just whether it's strong or weak. It's also dependent on the concentration. What we're looking at is the ability to transfer ions between two electrodes. Okay? If we have a weak acid, we don't have a lot of ions. But if we have a really concentrated weak acid, we may have a relatively smaller amount of ions, but there's still enough ions that we can allow for the transfer of electrons. Okay? So it's not just strong and weak, it also has to do with concentration, which now brings up a fun issue. How many of you have heard of molarity, our unit for concentration, before this semester started? 4 or 5 of you? Okay. Acids are kind of important, right? We don't want to splash acids on ourselves because we get burned. Okay? How many of you knew not to splash HCl on yourself before the class started? A substantial larger portion of you. Hopefully everybody knew that. Okay? We need to come up with some way that we can tell people to watch out for these species in some cases, but it's not all that important in other cases. Okay? And it's really coming down to this idea with our electrolytes. Strong and weak, but then also this concentration effect. But if we go through and tell our kids, you've got to watch out for a 1 molar solution, the first question we're going to get is why? We say, well, 1 molar has a lot of ions in it. Why do I care about ions? Okay? And you're going to run into this cycle. So one of the things we need to come up with is some way that we can compare these things, get us some kind of safety idea behind it, where we can say, if we hit this number, this one number is bad every single time. It doesn't matter if it's a strong acid, weak acid, any of these. If I hit that number, it is a bad solution. Do not splash it on yourself. Which comes back to the hydrogen ions. Well, a dilute strong acid solution is going to have a lot of hydrogen ions, where a concentrated weak acid could have that same amount. So if we look at our concentrations, it's not going to be perfect for us. So what we want to do is come up with another way to relate that information across without having to come through this concentration argument. Okay? And so those statements are kind of fun. We can't go shouting out, oh, watch out for that 0.15 molar solution. Okay? There's way too much to say in that. So what we developed instead was a way of monitoring our concentrations without having to bring in decimal values. You heard of pH before. Yeah. What's going on with pH? It's a measure of the concentration of hydrogen ions. Okay? I don't care where the hydrogens came from. They could be strong or weak acids. But if the hydrogen ions are there, that solution is dangerous. Okay? That's what our pH system does. It allows us to convert and get rid of the species and get us just to the one of the functionalities that is dangerous within that solution. Yeah? So let's take a look at what's going on with our pH scale. Anybody know the full scale for pH? 0 to 14. What does a 0 mean? Very acidic. What does a 14 mean? Base. Our pH scale is not just a measure of acids. It's a measure of both acids and bases. Okay? What's the pH of water? 7, dead center, which is our safety point. Okay? So if we're hovering around that 7 range, we aren't all that concerned about the solution. So that's what our pH scale does, is it converts our concentration of hydrogen ions across. And water, happening to be right in the middle, is a balance of what two species? What happens if we dissociate water into its ions? What are the ions that make up water? H plus and OH minus. What's the definition of an acid? H plus. Definition of a base? Or OH minus. Water is our perfect center. It gives us both species. So if we have a pH that's lower than water, that means we have an imbalance of hydrogen ions. If we have a pH that's higher than that of water, that means we have an imbalance of hydroxide ions. Both acids and bases are dangerous. All we want to do is center around that 7 level. So how do we get that number? Said it's a measure of the concentration, but our concentration unit is dealing with molar. How can we get our concentrations to always fall within this 0 to 14 range? Always in quotes. Because it doesn't. It's close enough. What we're going to have to do is do a slight conversion of our concentrations. Okay? Anybody know what the P means? Not urine. I need a drum roll all the time. It'd be fun. A little snare drum. Walk around with it in class. That P means negative log. Okay? Shows up a lot in 152. Okay? One of the reasons why people panic in 152. P just means negative log. So if I know the concentration of hydrogen ions and I want the pH, what do I need to do? The negative log of concentration of hydrogen ions. Okay? How do we do the negative log? With your calculator. Use your calculator. Your calculator will do it for you. What's that?
Coming from H negative?
H plus. It's always H plus. It's hydrogen ion. Yeah. Okay, so if I tell you the concentration of your solution is 0.15 molar, what is the pH? 0.82. All right. So you just punch in your calculator, negative log. Your calculator should give you parentheses. Put in the 0.15, and it'll spit out an answer. In this case, we said 0.82. All right. That's all you got to do to get your pH. Yes. What's that?
Bases can mesh up just as bad.
Just as bad. So when we teach our kids, so this is something that I find interesting, actually. I want to kind of understand the social ramifications of this. We talk to our kids about low pHs because they're acidic. Very rarely does anybody talk about bases. Bases are just as bad as acidic compounds. So when you talk to your kids, you say 7 is the good range. Keep it at a pH of 7. Anything higher or lower than that is bad. Okay? And that's what our pH scale is supposed to do. Why do we only talk about acids? I still don't understand that. I don't know why bases don't show up within that range. Because if you walked into a classroom and said, this is a strong acid, this is a strong base, you got to put your hand in one of them, everybody's going to put their hand in the base one. Okay? I said you have to put your hand in one of them. Okay? I don't know why that phenomenon is there. The only thing I can think of is that the acid was easier to discover. There's got to be some kind of history behind our acids. Okay? The other thing that you could think about, when you think about acids, what's the term? Okay? Those of you in my lab, what's the term that you should be looking for as far as safety goes for acids? Corrosive. If you look up the safety hazards for your acids, almost always they say corrosive. You almost always turn that into it burns you. That's fine. Okay, that's true. But what happens when you look up a base? Bases do the exact same thing to your skin as acids do. Within pain threshold, let's stick with that. Okay, chemically it's different. But if you look up a base, a strong base, they don't say corrosive. They say caustic. What's the net result? It burns you. Both of them do the exact same thing. We come up with a different name, and Thor, with a little bit of experience in industry, saying that if we're going to look at trying to store individual chemicals, we want to keep our acids separated from our bases. Why? What happens when we mix an acid and a base? It's a neutralization reaction, and what was the observation that we saw? Heat. If we happen to mix these two chemicals on very large scales, we're going to release a massive amount of heat. So if you happen to be the person mixing those two, now the solution is boiling with strong acids and strong bases. Okay? So a boiling, vigorous solution of acids and bases is a really bad experience. Okay? So when we talk about their hazards, we give their hazards different names so that people keep them separated from each other naturally without having to understand anything about the chemistry. Okay? So, questions about any of that? Okay. Well, in the next 10 minutes, I've got 40 slides to go through. No, just kidding. Do you guys have questions about anything in general?
So, what is the dissolves like rule?
Like dissolves like. I don't have that in. That might be a lie. Let's see if I can find that in the slideshow here. You might want to close your eyes if you're watching on the video.
This will be in the recorded slides.
Yeah, all of these slides are already online. There it is. And yeah, it's all recorded in the lecture video too. Solubility, like dissolves like. Okay? Our like dissolves like, remember, was horrible. We made an adjustment to that. It's not like dissolves like, it's like what? Forces dissolve like forces. So if we take a look at two compounds, take a look at H2O and CH4. What forces do we see in H2O? Hydrogen bonding. How do you know it's hydrogen bonding? Okay, we've got a hydrogen and oxygen, which means we have a polar covalent bond. Okay? Polar covalent bond gets us what force? Dipole-dipole. Do we have the potential for hydrogen bonding? What's the rule for hydrogen bonding? Dipole-dipole and hydrogen bound to oxygen, nitrogen, or fluorine. Do we have that in water? Yes. So we've got hydrogen bonding as our force for water. What's our force for CH4? What types of bonds do we have in CH4? It's a carbon and hydrogen bond, which is the bond is covalent. Okay, remember, you have to remember the definitions for each of these things. Our covalent bond leads to what force? London dispersion forces. London dispersion versus hydrogen bonding. Are those similar? Nope. Should they mix? No. Okay? So that's what's happening when we look at that like dissolves like. Let's tweak this a little bit more, make it a little bit more challenging. Let's say, oh, we could do a couple things here. CH3OH, CH3CH2OH, that's an O. I'm running out of space, and I can't go up higher. Let's do OH, CH2, CH2, OH. Looking at these dissolving in water, let's start with that first one, methanol. Should it dissolve in water? What's the intermolecular force? Strongest intermolecular force? We got our OH, which gives us hydrogen bonding. Is that similar to water? Yes. Should dissolve in water. What's the next one? Call it number 2. Should it dissolve in water? Yes. Which one should dissolve in water more, 2 or 1? Similar versus dissimilar forces. Our similar force is the same in both cases. What's our dissimilar force? CH3 versus CH3, CH2. What intermolecular force is generated in each of those? London dispersion. Should London dispersion forces dissolve in water? No. Which one has more of those bad forces? Number 2. That bad force means that they do not dissolve because they're dissimilar. Which one should dissolve more? 1. I thought it was pretty funny too. Last one. Call it number 3. Wow, still laughing. Should it dissolve in water? Why? Because of the OH. Should it dissolve more or less than 1 and 2? Why more? Still going. There's another hydrogen bonding interaction within that molecule. There are more hydrogen bonding interactions. That compound is more similar to water. It should dissolve the most out of those. Okay? So when you look at the questions on your test, on the multiple choice, it's usually what they're looking at. I think primarily you're just looking at the first 2 options, 1 and 2. Something similar like that and comparing it to water. After that, what you're probably looking at, take a guess. We could do CH3, CH3. Would we expect that to dissolve in water? Not at all. We could add another one, CH3O, CH3. That one's polar because of the oxygen. We do get that dipole force, but do we have hydrogen bonding? No. So if I've got to decide between these, which one's going to be the most soluble? Let me erase the ethanol for the moment. Which of those should dissolve the most? Number 1, our methanol with that hydrogen bonding. The other 2 won't dissolve as much, if at all. Okay? So when you see those structures, what you should be doing is not thinking in your head, this one's got this, oh, that's similar, this one's got this. Write it down. So our first one had what force? Hydrogen bonding. Next one had our London dispersion force, or LDF. Last one had a dipole-dipole. Which one is most similar to water? Hydrogen bonding, that's my answer. Less stuff to keep track of in your head. Please, for the love of whoever you want to, write stuff on the exam. Okay? Which kind of brings up another point. I will be posting the cover page for your exam so you can all read the directions ahead of time and you're aware of what's going on with it so you can effectively just write stuff down and move on. The next aspect that I want to make sure that you're aware of is that if you make a mistake on your Scantron on the previous exams, I did look for that. Okay? There were people that filled in the Scantrons in pen. Fun thing about pen, the machine doesn't read it. So I ran that machine, or that Scantron through and nearly had a heart attack because I thought someone got every single question wrong, and it freaked me out. Okay? I then went back and first off had to bubble in a new Scantron and put it in pencil. Okay? If that happens, I need something to be able to go to. With a pen Scantron, I can fill that in. What if you make a mistake bubbling in your Scantron? If it's in pencil, that's fine. It's at least red. But I've got nothing to check. So what I will end up doing, if I see a mistake on the Scantron, is go back to the exam booklet. Because I would hope in the exam booklet you've identified all of your answers. Most of you are not identifying your answers. So if you make a mistake in bubbling, there is nothing I can do. You lose whatever points at that point you effectively randomly guessed for the rest of your Scantron. So please, when you fill out your exam, mark your answers on the exam booklet as well in case there's a mistake in the Scantron. If you're one of those people that doesn't make mistakes, great for you. Just leave it on the Scantron. You'll get what you get. Okay? So please watch out for that when you go through and do your exams. I'm not going to ask that question. Yes?
I have a question about number 67 on the study guide about molarity.
67 on the study guide. Come on, give me a whiteboard. What is going on? Oh, I'm in a whiteboard. What is the molarity of a sucrose solution that contains 10 grams of, they aren't telling you that it's sucrose, but that is sucrose. 10.0 grams of C12H22O11 dissolved in 100.0 milliliters of solution. One extra piece of, well, we'll just pretend that you can't see that for the moment. What is the molarity of this solution? So, as with all problems, end with what you want. What do we want as our final answer? This is 67. We want molarity, which is moles over liters. Okay? Remember, when we talked about that there's two approaches. We can either solve for it all in one go, which usually gives people a bit of a heart attack with this one. So we can do it in 2 steps. Those 2 steps would be first, get the number of moles. Second, get the volume. And then your last step would be to divide those 2. Okay, so let's take a look at step 1. I want the moles of sucrose.
Is that 3.314 up top, or is that just 0.34?
There's no...
Like where you are up top?
Up top is in... Oh, I see what you're saying.
Is that...
That's 3,4. There's no 1.
That's the atomic mass and molecular.
Shh. We want the moles of sucrose. What are we starting with? Okay. We are starting with 10 grams of our sucrose. How do we get into moles? We need to get rid of our grams of sucrose, and we need moles of sucrose. Where do we get that information from? The periodic table. The test was nice enough for you. Where else can you get it from? The question. The question supplied it. It says that the molecular weight of that compound is 342.34 grams/moles, which means the number in front of grams is 342.34, and the number in front of moles is 1. Step 1 is solved for. We now have the moles of sucrose. What's step 2? Our answer needs to be the liters of solution. Are we given a volume? What is that volume? Whoops, I need to shift that a little bit. We're given 100.0 milliliters of solution. Is that our answer? No. What's wrong with it? It's in milliliters, so I need to convert it into liters. Where do milliliters show up? On the bottom. What shows up on top? What's the numbers that show up in front of these? 10 to the negative 3, and everybody's going the other direction, which I guess I should just accept. Milli means 10 to the minus 3. Okay, so 1 milliliter needs to be 10 to the minus 3 liters, because the little m means 10 to the minus 3. Okay? And you can do 1 liter over 1,000 milliliters. That is absolutely valid. It is the exact same number. I would argue it is not easier because of other conversions. I've noticed most people, if you do that, mess up the other conversions. Okay? So it's entirely up to you. It is the exact same calculation. There is no difference. That gets you your liters of solution. What's your answer supposed to be? It's supposed to be your moles of sucrose. Do you know that number? You just found it in your calculation, divided by your liters of solution. Do you know that number? Just found that in step 2. 1 divided by 2, and we've got our answer. That's not 0.5, by the way. Just wanted to clarify. That was another drum roll. We've got 1 minute left in class, so I'm fine to go ahead and end it. If you've got other questions, you can come up and ask. What? I don't remember. I've got 3 finals, and I keep shuffling all the times. It is correct on the syllabus. So what is it? 9 to 10:50 on Thursday of next week. The papers, the writing assignment, feel free to email those to me. I'm perfectly acceptable to accept them that way. Ideally, the earlier you email them, the better off you will be. Because then I can get through and grade them faster and get your grades reported a lot faster as well. Other questions? Your final is Thursday. There's no class next week. I will be holding office hours pretty much every day next week. Monday, it's going to be 9 to probably 12:30.